These notes are, they have a lot of math in them, okay? And you're going to have a quiz over these notes on Monday. Usually I give you a couple of days of class. So let me explain. The math is nothing more than multiplication and addition. So it's very like simple math stuff that you guys have been doing for years at this point. It's all about being super organized. So I'm going to have like meticulous order, and the practice problems I show you guys, you need to emulate that and have that same order. The people who do well in this quiz are always the ones who are the most ordered and organized. That's it. The people who are the most talented at math, oftentimes they skip a few steps and are not super organized, and they almost always make one or two mistakes. So it's all about being super organized. So don't worry too much about the math as long as you're organized. The other thing is, because I was sick, normally I give you 2 class days between the quiz and when you first learn it. But to compensate for the fact that it's only going to be 1 class day, I made sure you guys had this weekend of practice, and we're going to practice the first half of class on Monday and then take the quiz. So we're actually going to spend more time in class practicing this than we would have, and that's to compensate for the fact that you only have 1 day in between the notes and the quiz. Does that kind of make sense? So you're going to get a little bit more practice with me than you normally would. All right. So Thermochem notes number 5, the last notes of the unit for your unit test, which is Thursday and Friday of next week, little 2-day test. Energy associated with phase change notes. So 4.18 is fine for liquid water, but how about ice or steam? So 4.18 only works when you're talking about liquid water. Ice and steam are not the same. So to change 1 gram of water, 1 degree Celsius, you toss in 4.18 joules. To do the same thing with ice, you only need to throw in 2.06 joules. I would write this down because it will be useful later on in your notes. You will not have to memorize this number. You do not have to memorize that number, but I would write it down. Liquid water is the 4.18 that we're familiar with. And gaseous water is actually 2.02, slightly lower than the ice. And again, these 2 numbers right here, you do not have to memorize. I'll always provide them to you when you need them. But I would write them down right now because it'll be useful in your notes. So in terms of your little graph here, these apply to these 3 sections here in red. Or maybe if I change this up a little bit. So the red section, when you were warming up ice or cooling down ice, the 2.06 is your C. In green, when you're warming or cooling liquid water, you're using your 4.18. And in blue, when you're warming up or cooling down gas, you're using your 2.02. Okay? That's what we're looking for there. Now, here's one thing to note, though. That equation is Q equals MC delta T still. So you still use Q equals MC delta T. You're just going to use a different C for talking about ice or gas. Okay? Just going to use a different C, which you're used to. Like when you did a problem where like, hey, what's Q of this blah, blah, and the C of this silver is 0.240. Like you're used to using a different C. Here's a question, though. Q equals MC delta T. It's great for each phase of matter, but it's not so good for a phase change. So remember when we're changing phase is when the graph flattens out right there and right there. How come Q equals MC delta T doesn't work well for those 2 sections highlighted? Yeah, Jameson?
It doesn't change.
The temperature doesn't change. You don't have a delta T for those sections, right? Melting ice is always exactly 0 degrees Celsius. And so there's no temperature change, and so that causes a problem. So we need to learn how to calculate the Q for these 2 flat sections highlighted in yellow. Bless you. Which is what we're about to do right now. Double bless you. A little greedy with the bless yous, huh? Okay, so let's talk about during a phase change. You'll use this equation. Q equals M times delta H. It's actually a little simpler than Q equals MC delta T. So Q will just equal M times delta H. M is your mass. Okay, that's a mass. So that's the same as always. You can just go ahead and put that on my keyboard. And delta H will be a given value. Delta H will be a given value. Delta H will be a given value. So Q equals M delta H applies to these 2 sections right here on the graph. They have special prices. I call these both bridges. You guys ever been on a toll road where it costs like a certain amount of money to continue on that toll road, okay? So there's a certain price to go across each bridge. And we're going to talk about those prices. So, to go across the lower bridge, we call that heat of fusion. So this is at 0 degrees Celsius. So when you're either melting ice or you're freezing water. The heat energy needed to melt or freeze 1 gram of a solid at its melting point, solid water that is, will be Q equals M delta H, and we say fusion. So that lower bridge is called the fusion bridge. And that price, which you do not have to memorize, I would write it down, but you do not have to memorize it, is 334 joules per gram. That's the magic number, 334 joules per gram. That is just the cost to go across the lower bridge, the fusion bridge. And so, for example, let's say Jameson wanted to melt 100 grams of ice. That was at exactly 0 degrees Celsius, so like it was just ready to start melting. Okay? So he wants to go from this bridge, he wants to go from here to here on the bridge. It's a very simple calculation. Q equals M delta H. Well, his M is 100 grams. His delta H is just simply that price, 334. You multiply those together, and you get 100 grams of ice melted completely will cost you 33,400 joules. And that's all she wrote. That's it. Just multiplying M and your H value, which will be given to you, the 334. Never have to memorize that, but like I said, I would write that down because it's quite useful in your notes. Okay, so that's the lower bridge. That's the cheap bridge. The other bridge is called the heat of vaporization, so this is happening at exactly 100 degrees Celsius. Heat of vaporization happening at exactly 100 degrees Celsius. So that is when you are vaporizing a liquid. So you're taking it from the liquid stage to the gaseous stage, or to the gas stage, or you're taking it from the gas and you're condensing it to liquid. So you're adding energy if you're vaporizing, you're taking energy away if you're condensing. So the heat energy needed to vaporize or condense 1 gram of liquid at its boiling point. The equation for that is Q of vaporization equals M times delta H of vaporization now. So for water, the price to go across the expensive bridge is 2,260 joules for every single gram you're carrying across that bridge. It's really expensive. It's really expensive. Very expensive price. Again, don't have to memorize that, but I would write it down. It's a huge cost. So, for example, let's say we had those same 100 grams, and they're at exactly 100 degrees Celsius. So we have some liquid, 100 grams of liquid water, and we want to go across this bridge. So every last drop of that has just evaporated, but still at 100 degrees. Here's the cost. So your Q in that situation would equal your mass, which is 100 grams, times the price of the expensive bridge, which is 2260. So to boil 100 grams of water, you would have to add 226,000 joules just to boil 100 grams of water. You guys were boiling like 250 grams of water during your bolt lab. So you put a whole lot of energy into that water, which is why the 3-finger flame is so important, because it's going to maximize your joules you're sending in there per minute. Okay? Now, here's where this all comes into play, and here's where the organization is key. I really can't emphasize enough how important it is to just be like over the top organized for these problems, and you'll see me do that. Here's your problem, so write that sentence down. How much energy is required to warm 265 grams of ice at negative 15.4 degrees and to make it steam at 185 degrees Celsius? What is the price to go all the way up there? All right, now here's what I like to do. I like to draw this graph all the time. Hey, remember, if you want to reproduce this graph on your own, because I would say it's pretty helpful, here's how you do it. Boom, boom, boom. Up, flat, up, flat, up. What temperature is the first bridge at? Temperature of the second bridge? 100. There you go. You reproduce this graph. Okay? Anyways, I'm going to use my, oopsie, that's not what I want to do. I'm going to use my one that's already on there. But you guys can reproduce your own on your worksheets whenever you want. All right, now, where is negative 15.4 degrees ice? Where would that be on this graph? The very bottom. It'd be somewhere around here, right? Where would 185 degrees gas be? Wait, at the very top. It'd be somewhere around here. So I got to go from point A to point B. Let's break that down. Okay. So that very first section, I need to warm that ice up to the point where it could start to melt. I need to warm that ice up to the point where it could start to melt. Stop that. I don't know why it's doing that. My smart board. So I need to calculate my first Q here. And I need to break them up into different sections because there are different prices associated with each one. So just going from here to here. I'm just going from here to here right there. So is there a change in temperature for that section? Come from here to here? Yes, there is. Okay, so I'm going to use Q equals MC delta T. So my M is 265 grams. You'll notice that all of these will start with 265 grams because your mass isn't changing. What is my C for ice? 2.06. 2.06, and he's getting that from right over here. Everything I'm highlighting here in green will be on like your quiz. It's the same exact little chart. Okay, so you're going to use 2.06 because you're talking about ice. And how much is the temperature changing in just this section? How much is that temperature changing? How much are we warming the ice? 15.4 degrees. Some people are going to be like, wait, do I have to find the difference between 15.4 and 185? No, because we're not going up to 185 yet. We're going to break our delta T's into little segments, okay? So we're just changing it 15.4 degrees because we're just trying to get it up to 0, okay? The next step is we're going across the cheap bridge right here. Cheap bridge. So that is just melting. We're just melting right there, the ice. Is there a delta T associated with this second step? Is there? No, it's a flat line. It's all at 0 degrees, so we can't use Q equals MC delta T. We're going to just use Q equals M delta H, so your M, 265 again. Stop doing that, smartboard. 265. What is the price to go across the cheap bridge? $3.34, right? $3.34. So there you go. There's that. Now our next section, we're going from here up to here. So that is all liquid water, and we're just warming it up. That's all we're doing with our liquid water. So is the temperature changing? Yes. Q equals MC delta T, business as usual. Our M is 265. What is your C for liquid water? 4.18. That's just our usual. We're used to him. And how much is the temperature changing in just this section? So we started right here for this third section, and we went to here. How much is the temperature changing in that section? Just 100 degrees, right? And so we're getting another 100 of our delta T calculated in. Now we're going from this guy to this guy. We're going across the expensive bridge now. So we need to boil that water. Is this an M equals M or Q equals MC delta T or Q equals M delta H? M delta H. Why? Because there's no what? There's no temperature change. That's right. So M 265. What is the price to go across the expensive bridge? 2,260. That's all you got to plug in there. And then lastly, we got to go all the way up to this last section right here. So we got to warm that gas up. So we're warming your gas up to 185 degrees. The mass is still 265. What is the C for gas? 2.02. Yep, 2.02. And then how much is the temperature changing in this last section? 85. You're going from 100 up to 185. So it's just changing E5. So you have 5 Qs. Notice how I labeled them. I was super clear. I have nice separated lines. Now I'm going to add them all up. That comes out to be a little over 8,000. That one's about 88,000. Going across the bridges is pretty expensive. Warming up that water is 110,000. The most expensive price will always be going across the expensive bridge. That's 598,000. And to warm that gas up at the end, that's another 45,000. You add all those up for the total price of this road trip, and we got 852,087.4 joules. The model student, of course, would never dream of not boxing that up for me. Boom. It is all about organization. Yes, sir.
What temperature does water boil in Fahrenheit?
212. Yep. Okay. So now we're going to move on to this worksheet right here. This guy. The quiz is not Thursday. It's going to be on Monday. It's going to be on Monday. So you'll notice I have one of these graphs here on the right. It helps make my life easier. I strongly suggest you get used to drawing those graphs. You never have to, but it just makes your life so much easier if you're super familiar with drawing those graphs. Again, it's just get the axes. Up, flat, up. 0. 100. That's really suspicious 0, but you guys get the idea. Anyways, I've got one printed on there. So, heat of fusion, remember, is just when you're melting or freezing at 0 degrees. Heat of vaporization is when you're boiling or condensing at 100 degrees. All right. When you're warming or cooling, you're using Q equals MC delta T, and you're using Q equals M delta H. A little H got cut off here when you're going across a bridge. All right. In this first problem, calculate the number of joules needed to turn 525 grams of water at 100 degrees to steam at 100 degrees. So I'm going to find where I'm starting on my graph. Where is liquid water at 100 degrees on this graph? Where would that be? Right before the what? Which flat part? Yes, it'll be right here. Not on the other side because it's liquid water, right? So that water hasn't boiled yet on the left. We're going across to this side, and we're just stopping right there because it's still at 100 degrees steam, it says at the end. So this is just a 1Q problem. We just got our 1Q right there. So this will be relatively short, okay? So I can count how many Qs I got. So first thing I got to do is I just got to vaporize. So I have 525 grams. Is this Q equals MC delta T or Q equals MH? MH, right, because there's no delta T. What's the price to go across the expensive bridge? Yep, so 2,260. Again, he's getting that from right here. You never have to memorize these numbers. Okay, that will be provided to you on your test or quiz. So you just plug that in. Comes out to be 1,186,500 joules. Boxing it up. And that's that. And I knew ahead of time, just by looking at my graph, I was only going to have to calculate 1Q. I'll get the next one started for you, and then you'll work on your own, and I'll come around and check in. So calculate the heat needed to change 15 grams of ice at negative 50 degrees to 50 grams of water at 50 degrees. Well, where am I starting on this graph? Where on this graph would I start? Where is negative 50 degrees ice? All the way down here somewhere, right? I don't know exactly where. It doesn't matter. I just know it's below the 0, so I'll put below 0. Where's 50 degrees of liquid water? Yeah, somewhere around there. Okay? How many Qs will I need? You can count right now. 1 Q, 2 Qs, 3 Qs for 3 different sections of the graph. So you're going to have to calculate 3 Qs, so this will be a 3Q problem. If I were you, I just like to kind of write my Q1, Q2, Q3, get those all set up ahead of time. So I'm super organized, and I don't mix anything up. So that is your energy calculations involving phase change practice. You will practice the rest of this period. I would do some practice over the weekend, like maybe on Saturday or Sunday, something like that. You got a nice long weekend, do a few problems. On Monday, you'll come in. We'll do a few more practice problems on a new worksheet. And then you guys are going to take your quiz the second half. Okay? All right, let's get cooking.